The two-slit experiment. Well, if you demand that your theory have local beables, which are supposed to explain results of quantum measurements and everything else we see around us, and you don't have a lot of imagination, you are immediately led, I would say, to Bohmian mechanics. How do you get to Bohmian mechanics from the usual theory? You let yourself be, just follow the language. In standard quantum mechanics, you talk about particles. If you're not imaginative, you'll say particles means particles, things with positions. So you'll say that in addition to the wave functions, you have particles, things with positions, so that the complete description of the system will involve its wave function together with the positions of its particles. So the crucial idea of Bohmian mechanics is utterly trivial. Particles means particles. That's an idea, it's not a theory. To have a theory, you need evolution equations. You have one for the wave function, Schrodinger's equation. And as soon as you look for an equation for the particles, you ask for what's the simplest kind of evolution equation you could have for the particles. Almost any way you think about it, there are by at least 10 different routes, you're led to the same equation, which you've seen many times, actually written in at least 3 different ways here. And so then you get to Bohmian mechanics, concerning which I want to say right now very little more. I simply want to give a nice Bell quote, which has it, I don't think it's been used here, about the two-slit experiment. In the quote, Bell is referring to the pattern of trajectories that you get in the two-slit experiment for Bohmian mechanics. All of you have seen it. Maybe some of you have just seen it for the first time here. I doubt it. I think you've all seen it before. Here's what Bell says. Is it not clear from the smallness of the scintillation on the screen that we have to do with the particle? So what's happening here? When you do the experiment, particles arrive one at a time, if you do it at low intensity, one at a time at a screen, and a dot appears. So first you have a dot somewhere, then a dot somewhere else, then a dot somewhere else. You get a pattern. The pattern of dots corresponds very well to the pattern of trajectories you see here. Is it not clear from the smallness of the scintillation on the screen that we have to do with a particle? And is it not clear from the diffraction and interference patterns that the motion of the particle is directed by a wave? De Broglie showed in detail how the motion of a particle passing through just one of 2 holes in the screen could be influenced by waves propagating through both holes, and so influenced that the particle does not go where the waves cancel out, but is attracted to where they cooperate. This idea seems to me so natural and simple. To resolve the wave-particle dilemma in such a clear and ordinary way that it is a great mystery to me that it was so generally ignored. And it should be a mystery.
You have answered why it was generally ignored.
Go ahead.
Because people are idiots.
Next. Naive realism about operators. What is that? You heard about it before from Damiano and Andrea. That's actually a real problem, naive realism about operators. It infects is probably not a strong enough word, so much thinking about foundations of quantum mechanics. When you hear people say that in quantum mechanics we need a new logic, it's because of naive realism about operators. When you hear people say that to understand quantum mechanics you have to use a non-Kolmogorovian probability, that's because of naive realism about operators. Almost all the weird stuff people say, not non-locality, but all the other weird stuff, is because of naive realism about operators. What is naive realism about operators? It means taking the language in quantum mechanics about operators as observables too seriously. To think that if you have that a self-adjoint operator, what is the language we use in quantum mechanics? We are told at square one that the observables in quantum theory are operators, self-adjoint operators, and people are often very happy because it sounds very deep. Now we know what the observables are. Now we know what the physical quantities are. Isn't it great that we have some precise mathematics which picks out for us what the physical quantities are? The problem with it is that these are not physical quantities at all. These are just objects which are useful for the description of many, many experiments. Yet, one of the common objections to Bohm is that, okay, you can handle positions, but what about all the other observables? Don't you need to make real in the same way that you made position real by assuming that the position has a value at every instant? That's what the theory says. You have particles with positions. Shouldn't every other quantum observable, every self-adjoint operator have a value at every time? This really appeals strongly to students of quantum mechanics, and it is complete foolishness. If you wanted to, you could actually write down some equations. You could add extra variables corresponding to all the other operators and even give them a dynamics. And all you would have served to do is complicate the theory. It would have been utterly pointless to have done so. Here's some Bell on it. So first, it was a fragment of what I quoted before, sort of conveying a bit of an edge in Bell's when he refers to observables. The observables of other formulations of quantum mechanics for which we have no use here. Final moral concerns terminology. Why did such serious people take so seriously axioms which now seem so arbitrary? He's referring here to the measurement axioms. The axioms about measuring all the observables. I suspect that they were misled by the pernicious misuse of the word measurement in contemporary theory. And you could also say pernicious misuse of the word observable, because these words go together. Measure, you measure observables. Measure, if measurement is being misused, so is observable. This word very strongly suggests the ascertaining of some pre-existing property of something, any instrument involved playing a purely passive role. Quantum experiments are just not like that, as we learned especially from Bohr. The results have to be regarded as the joint product of system and apparatus, the complete experimental setup. But the misuse of the word measurement makes it easy to forget this and then to expect that the results of measurements, in quote, because they're not really measurements, should obey some simple logic in which the apparatus is not mentioned. The resulting difficulties soon show that any such logic is not ordinary logic. It is my impression that the whole vast subject of quantum logic has arisen in this way from the misuse of a word. For Bell, the word measurement, but also the word observable. I am convinced that the word measurement has now been so abused that the field would be significantly advanced by banning its use altogether in favor, for example, of the word experiment. I really feel that if every person working in foundations of quantum mechanics took this to heart, the field would be enormously improved. In physics, the only observations we must consider are position observations, if only the positions of instrument pointers. Bell is not saying that the only things we can measure are positions. He's talking about the fact that at the end of the day, when you finish the measurement, you're going to have something positional, like a pointer pointing, which registers the result. It is a great merit of the de Broglie-Bohm picture to force us to consider this fact. If you make axioms rather than definitions and theorems about the measurement of anything else, like the other observables, like you do in orthodox quantum theory, then you commit redundancy and risk inconsistency. Students, how many of you understand this statement? Raise your hands. How many of you don't understand this statement? Please, raise your hand. How many of you don't know whether you understand this statement? Oh, you guys are scared. Look, I don't think you all understand this statement, and my point here is to suggest to you very, very strongly, think about it until you really do understand it, because then you will really understand something important. think I want to skip most of them. Well, there's plenty of time. That X rather than psi. So X refers to, let's say, this is probably referring to Bohmian mechanics, but I'm not even 100% sure. I think it is. X is the positions of one or more particles. That X rather than psi is historically called a hidden variable. Okay, so this is related to the red and hidden. That X rather than psi is historically called a hidden variable, is a piece of historical silliness. From the microscopic variables X, little x, X now, so the X here was, I guess, macroscopic. Little x microscopic. From the microscopic variables, little x can be constructed macroscopic variables capital X. So capital X is some function of the little x's, the positions of all the particles, say. Including in particular, so the macroscopic variables could be, including in particular instrument readings, image density on photographic plates, ink density on computer output, and so on. Of course, there is some ambiguity in defining such quantities. For example, over precisely what volume should the discrete particle density be averaged to define the smooth macroscopic density. However, it is the merit of the theory that the ambiguity is not in the foundation, but only at the level of identifying objects of particular interest to macroscopic observers. And the ambiguity arises simply from the grossness of these creatures. It is thus from the x's, the microscopic variables, rather than from psi, that in this theory we suppose, quote, observables to be constructed. It is in terms of the x's that we would define a psychophysical parallelism if we were pressed to go so far. Thus, it would be appropriate to refer to the x's as exposed variables and psi as a hidden variable. It is ironic that the traditional terminology is the reverse of this. There's something, you might have found something a bit weird here. Why all of a sudden, out of the blue, a reference to psychophysical parallelism? Now, Bell wasn't crazy, and he was a good writer. There was a reason for it. I'll come to it a little bit, touch on it. But I do want you to notice that somewhat strange allusion there. Should seem strange to you. All right.